We've looked at forces in both vertical and horizontal directions on turning circles. Now we're going to kind of go into both dimensions at the same time. We're still turning a horizontal curve, but this time we're going to look at it at a bank. And what I mean is we've looked at in the past, we've seen roads that have just curved around to the side. But in reality, this is almost never horizontal, flat. It's usually actually turned up at an angle. And I'm exaggerating here. Our angle's not really that high. Let me draw that a little nicer. But if you were looking in from the back as this car's going this way around the corner, if we looked at it from behind, we would see that the road's actually curved in, so that as it curves around this way, there's a ramp here, and the car sits right here and goes around the corner this way. Okay? So we want to actually figure out what forces are acting on that car on the ramp. So the easiest way to do that is to do that from the straight from the back. Okay? So we're looking straight on from the back, car is sitting right here on this banked curve. It's driving into the screen and turning to the left away from us. So the center of the curve is somewhere over here. Now generally when we do this we say, well, the motion is down the ramp, so we're going to put our reference frame so that acceleration is down the ramp. But this time our acceleration is not down the ramp, because we're still turning this curve at a constant speed. It's uniform circular motion, which means the only acceleration we have is centripetal acceleration, and it is towards the center of the circle. So we don't pick our reference frame directed along the ramp. We pick our reference frame so that the positive x direction is towards the center of the circle. So when we have a car turning an incline, I'm going to draw this one more time, we actually have to consider several forces that are going into this, and there's a thing called a design speed where we can ignore friction altogether. But let's just say my car's here. Alright, so we're looking at the two tires from our car on the rear side, and then, alright, looking at my car. Now, like I said before, center's this way, and if we look at our forces, we still have force due to gravity, Fg. We still have the normal force, Fn, and then there's friction. But I don't know which way is friction acting, because if this car's going too fast, then it's going to try to go up the incline. It's going to try to drift up the incline, and so friction will try to oppose it and come this way. If it's going too slow, then it tries to drift down the incline, and friction will oppose it and move up the incline. So what I'm going to look at is just a case where we have friction, and I'm going to say that the car tends to be going too fast. So I'm going to say that there's a frictional force. Now friction always acts parallel to a surface, perpendicular to the normal force. So I'm going to say that the friction is actually acting down the incline. Now this is the important part of drawing a picture. When you have all these forces on here and we have our reference frame, you have to be able to consider positive, negative, and x and y. So y, positive direction, is that way, and since the center of my circle is here, center, I'm going to have the x positive direction towards that. So when I look at this, I'm actually going to have to find components of some of these forces. I'm going to have to find components of the normal force, which is going to have an x and a y component. So this is Fnx, and this is Fny, and I'm going to have to find components of friction, because friction will also have components that act in x and in y. So here's Fx, Fsx, and static friction, Fsy. Now if I want to know all the things about this thing, let's say that this thing is turning this corner, it has radius r, it has incline theta, and the car is traveling with speed v, and the coefficient of friction is just the coefficient of friction. Okay, so I'm not going to give values to any of these things. I just want to see if I wanted to find how big the normal force, how would I go about doing that? If I wanted to find how big the frictional force is, how would I go about doing that? So I do that the same way I've always done it. I'm going to go into the x and y directions, the net force in x and the net force in y. And what I said earlier about keeping track of positive and negative, this is where that's going to matter a lot. Now the very first thing I want to notice is that in y, this car, we don't want it to drift up or down, it's just going around the curve. So the net force in y has to equal 0. And from that, I can determine a whole bunch of things. I can say, well, what forces act in y? And be careful, there are 3. There's the normal force in y, there is friction in y, and there is gravity in y, but they do not all act in the same way. The only positive force in y is the normal force in y. So Fn y plus a negative Fsy. I'm going to keep track of sign for myself. I'm going to rely on the picture for that. So the static friction in y is negative because it's pulling down, and then plus negative Fg because it is also pulling down, and that's going to sum up to 0. Okay, so that's the sum of my forces in the y direction. Okay, the static friction having a component is a new thing for us. Now, in the x direction, this is going to work a little bit differently because our acceleration is towards the center, so the net force in x is actually m AC, because the only acceleration I have is the centripetal acceleration. Okay, so the car has mass m too, I guess. Now, if we go into the x direction, positive x is, remember, towards the center. There are 2 forces that are helping this thing go towards the center. There's static friction in x, and there's the normal force in x. So I have Fnx plus Fsx, the static friction in x, the normal force in x, that equals m AC, and that's our net force in the x direction. Now, we have to be very, very careful. The things we have to be very careful about are the fact that the normal force is not balancing gravity. The y component of normal force is not balancing gravity. We know some angles, but we've got to be careful with them. Okay, so if I wanted to know the normal force, if I'm solving for the normal force, then the normal force appears here and here, except those are x and y components. So remember, if this angle right here is the angle theta, then it turns out this angle up here is also the angle theta, and this angle right here for the static friction is also theta. Now that means you got to pay attention to sine and cosine and what's going on. So if I was going to rewrite this in terms of all the magnitudes of friction in the normal force instead of the components, then what I have is this side, the y side of my normal force is actually adjacent to that angle. So I have the normal force in y is equal to the normal force, whatever it is, times the cosine of the angle. And if I want the static friction in y, then static friction in y is actually equal to the static friction times, and this is opposite that angle, so that's times the sine of theta. So since we're dealing in multiple triangles, multiple dimensions, you have to pay attention to your trig. So I could rewrite this equation down here as Fn cosine theta plus Fs sine theta, but remember this one's negative because it's pulling down, minus Fg equals 0. So I haven't changed that, I've just gone ahead and moved it into the components, or the magnitudes with the sine and cosine. And then on the x side I can do the same thing, but now the normal force, the x component, is opposite that angle, so I'm going to have Fn times the sine of theta plus, and this one is adjacent, the friction is adjacent, Fs cosine theta equals MAC. And by keeping track of all the forces that are acting in all the different directions, we are able to solve this problem. We could either find the normal force or we could find friction or whatever, but it's a matter of not making poor assumptions. We can't assume that the normal force is equal and opposite to gravity here, because it's not, because there's multiple forces acting in the y direction. We have to keep track of all the forces.